What if I told you that the faint glow you see on an old, static-filled television screen is actually a glimpse into the birth of the universe? That's right, what looks like random noise is the cosmic microwave background, the oldest light in existence, and it's been traveling through space for over 13.8 billion years. This ancient light is like a cosmic time capsule, holding secrets about how everything we know, stars, galaxies, even you and me, came to be. And today, we're diving into 25 mind-blowing facts about this incredible phenomenon that will completely change how you see the universe. From accidental discoveries to mysterious ripples that map the early cosmos, this is your ultimate guide to the cosmic microwave background. So, buckle up, because by the end of this video, you'll see the universe in a whole new light. Let's get started. Now, let's dive into the first incredible fact about the cosmic microwave background. The CMB is the oldest light in the universe, a relic from the very beginning of everything. Picture this: 13.8 billion years ago, the universe was born in a fiery explosion known as the Big Bang. In those first moments, the cosmos was a seething, chaotic soup of energy and particles. But as the universe expanded and cooled, light was finally able to travel freely. This light, released when the universe was just 380,000 years old, is what we now detect as the cosmic microwave background. It's like a snapshot of the universe in its infancy, frozen in time and still traveling across the cosmos. What makes this light so special is that it's the farthest back in time we can see. Every other form of light, from stars, galaxies, or quasars, comes from much later in the universe's history. The CMB is our direct line to the dawn of creation, a glowing echo of the Big Bang itself. And here's the kicker: this ancient light is everywhere. No matter where you look in the sky, the CMB is there, a faint whisper from the universe's earliest moments. It's not just light, it's a time machine allowing us to peer back billions of years and witness the birth of everything we know. So the next time you hear about the CMB, remember, you're not just looking at light. You're looking at the universe's very first glow. Now, let's shift gears to another fascinating chapter in the story of the cosmic microwave background, one that involves a bit of serendipity. The CMB wasn't discovered through a grand, deliberate search for the universe's oldest light. Instead, it was found entirely by accident. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to calibrate a sensitive radio antenna. Their goal was to study radio waves from space, but they kept picking up a persistent, mysterious noise. No matter where they pointed the antenna, this faint, static-like signal was always there. At first, they thought it might be interference from nearby New York City or even from the antenna itself. They checked every possible source of error, even cleaning out pigeon droppings from the antenna, thinking that might be the culprit. But the noise remained. Frustrated but determined, they eventually realized this wasn't just random interference, it was something far more profound. What they had stumbled upon was the cosmic microwave background, the faint afterglow of the Big Bang. Their accidental discovery not only confirmed a key prediction of the Big Bang theory, but also earned them the Nobel Prize in Physics in 1978. It's a perfect example of how sometimes the most groundbreaking discoveries come from the most unexpected places. And to think it all started with a little noise and a lot of pigeons. Now let's take a closer look at one of the most intriguing aspects of the cosmic microwave background, its near-perfect uniformity, but with a twist. When scientists first mapped the CMB, they were struck by how incredibly even it appeared across the entire sky. This uniformity was a big deal because it supported the idea that the early universe was remarkably smooth and consistent. But here's where it gets even more fascinating. Upon closer inspection, they noticed something extraordinary: tiny, almost imperceptible variations in temperature. These fluctuations, as small as 1 part in 100,000, might seem insignificant at first glance, but they hold the key to understanding how the universe evolved. These slight differences in temperature are like cosmic fingerprints, marking the seeds of all the structure we see in the universe today. They represent the denser regions where matter began to clump together, eventually forming galaxies, stars, and even the vast cosmic web that connects everything. Without these tiny irregularities, the universe would have remained a featureless sea of particles, and we wouldn't be here to talk about it. So, while the CMB appears almost perfectly uniform, those subtle variations tell a story of how the universe went from smooth to structured, setting the stage for everything that followed. It's a reminder that sometimes the smallest details can have the biggest impact. Now, let's shift our focus to something truly groundbreaking: how the cosmic microwave background serves as one of the most compelling pieces of evidence for the Big Bang theory. Imagine trying to piece together the story of the universe's birth. It's no small task, but the CMB gives us a direct line to that moment. When the universe was just a few 100,000 years old, it was a hot, dense soup of particles and energy. As it expanded and cooled, light was finally able to travel freely, creating the first glow of the cosmos. That glow is what we now detect as the CMB. But here's the kicker. This ancient light doesn't just tell us about the universe's early days. It confirms that the Big Bang actually happened. The uniformity of the CMB, combined with those tiny temperature fluctuations we talked about earlier, matches predictions made by the Big Bang model. If the universe hadn't started with a massive explosion, the CMB wouldn't look the way it does. It's like finding a fossil that perfectly matches the description of a long-lost species. It's proof that the theory holds water. Scientists have spent decades studying the CMB, and every observation has only strengthened the case for the Big Bang. It's not just a theory anymore, it's a cornerstone of modern cosmology. So the next time you hear about the Big Bang, remember, it's the CMB that gives us the confidence to say, yes, this is how it all began. And with that, we're ready to dive into the next chapter of this cosmic story. Now, let's take a step back in time, way back to when the universe was just a newborn. The cosmic microwave background isn't just a relic of the Big Bang, it's essentially a baby picture of the cosmos. Imagine the universe at just 380,000 years old. At that point, it was a completely different place, hot, dense, and filled with a swirling sea of particles and energy. But as the universe expanded and cooled, something incredible happened. For the first time, light could travel freely, breaking free from the fog of particles that had trapped it. This moment, known as recombination, marked the birth of the CMB. What we're seeing when we observe the CMB is that very first light, a snapshot of the universe at that precise moment. It's like opening a time capsule and finding a photograph of the universe in its infancy. This ancient light carries with it a wealth of information about the conditions of the early universe. It tells us about the temperature, the density, and even the distribution of matter at that time. Those tiny temperature fluctuations we've mentioned earlier. They're like fingerprints, revealing the seeds of all the cosmic structures we see today: galaxies, clusters, and even the vast cosmic web. By studying the CMB, we're not just looking at a picture, we're decoding the universe's first chapter, written in light. And as we continue to explore this cosmic snapshot, we uncover more about how the universe evolved from those early moments to the vast, complex cosmos we know today. With that in mind, let's turn our attention to another fascinating aspect of the CMB: its temperature, and why it's one of the coldest things in the universe. Now, let's shift our focus to something that might surprise you: just how cold the cosmic microwave background really is. At a mere 2.7 Kelvin, or around -270.45 degrees Celsius, the CMB is one of the coldest things in the entire universe. To put that into perspective, outer space itself is already frigid, but the CMB is even colder. This temperature is a direct result of the universe's expansion over billions of years. As the universe stretched and grew, the once hot radiation from the Big Bang cooled down, leaving behind this faint, cold glow that we now detect as the CMB. But why does this matter? Well, this extreme coldness is a crucial piece of evidence supporting the Big Bang theory. It tells us that the universe has been expanding and cooling since its fiery beginning. And here's something even more fascinating: this temperature isn't just a random number. It's a precise measurement that helps scientists understand the universe's thermal history. By studying the CMB's temperature, we can trace back the conditions of the early universe and see how it evolved into the vast, structured cosmos we observe today. So, while the CMB might be incredibly cold, it's also incredibly important, offering us a window into the universe's past and helping us piece together its incredible story. With that in mind, let's move on to another intriguing aspect of the CMB: its omnipresence, and why it's literally everywhere in the universe. Now, let's take a step back and consider something truly mind-blowing. The cosmic microwave background isn't just a distant relic of the past, it's literally everywhere. No matter where you point a telescope in the sky, you'll detect the faint glow of the CMB. This is because the CMB is the afterglow of the Big Bang, and it fills the entire universe like a cosmic echo. Think of it as the universe's oldest and most widespread wallpaper, stretching across every corner of space. But how is this possible? Well, when the universe was just 380,000 years old, it transitioned from being opaque to transparent, allowing light to travel freely for the first time. That light, now stretched and cooled by the expansion of the universe, is what we see as the CMB. It's not just in one direction or one region, it's in every direction all around us. This omnipresence makes the CMB a universal phenomenon, a constant reminder of our cosmic origins. And here's the kicker: because the CMB is everywhere, it serves as a kind of cosmic reference point. Scientists use it to map the universe, measure its expansion, and even study the distribution of galaxies. So, while the CMB might seem like a faint, cold glow, its ubiquity makes it one of the most powerful tools we have for understanding the cosmos. With that in mind, let's turn our attention to another fascinating aspect of the CMB: how it reveals the universe's composition, including the mysterious dark matter and dark energy that make up most of our cosmos. Now, let's dive into something truly fascinating: how the cosmic microwave background acts as a cosmic recipe book, revealing the ingredients that make up our universe. You see, the CMB isn't just a snapshot of the early universe, it's also a treasure trove of information about what the universe is made of. By studying the tiny temperature fluctuations in the CMB, scientists can figure out the proportions of dark matter, dark energy, and ordinary matter that fill the cosmos. Here's how it works: those tiny ripples in the CMB, known as anisotropies, are like fingerprints left behind by the early universe. They tell us how matter was distributed when the universe was just a baby. And because gravity has been shaping the universe ever since, those patterns have grown into the galaxies, stars, and planets we see today. But here's the kicker: most of the universe isn't made of the stuff we can see. In fact, ordinary matter, the atoms that make up you, me, and everything we can touch, accounts for only about 5% of the universe. The rest, that's where things get mysterious. Dark matter, which makes up roughly 27% of the universe, doesn't emit light or interact with electromagnetic forces, but it has gravity. We know it's there because it bends the light from distant galaxies, a phenomenon called gravitational lensing, and it influences how the CMB's patterns evolve over time. Then there's dark energy, the most enigmatic of all. This invisible force makes up about 68% of the universe and is responsible for its accelerated expansion. The CMB helps us measure this expansion and gives us clues about how dark energy behaves. So, in a way, the CMB is like a cosmic detective, helping us piece together the universe's composition. It's not just about what we can see, it's about uncovering the hidden forces and materials that shape everything around us. And as we continue to study the CMB, we're getting closer to understanding the true nature of these mysterious components. With that in mind, let's explore another intriguing aspect of the CMB, the tiny ripples, or anisotropies, that hold the key to mapping the early universe's structure. Now, let's zoom in on one of the most fascinating features of the cosmic microwave background, those tiny ripples known as anisotropies. These subtle temperature variations might seem insignificant at first glance, but they're actually the key to understanding how the universe's structure began to take shape. Think of them as the universe's first whispers, carrying secrets about its earliest moments. These anisotropies are incredibly small, with temperature differences of just a few millionths of a degree. But don't let their size fool you, they're packed with meaning. Each ripple represents a slight difference in density in the early universe. Where the temperature was slightly higher, there was a bit more matter. Where it was cooler, there was a bit less. Over billions of years, gravity amplified these tiny differences, pulling matter together to form galaxies, stars, and eventually the vast cosmic web we see today. What's truly remarkable is that these anisotropies aren't random. They follow a specific pattern, almost like a cosmic fingerprint. By studying this pattern, scientists can map out how matter was distributed when the universe was just 380,000 years old. It's like having a snapshot of the universe's blueprint, showing us where everything began. But the story doesn't end there. These ripples also help us test theories about the universe's origins. For example, they provide strong evidence for cosmic inflation, the idea that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The anisotropies' scale and distribution match what we'd expect if inflation really happened, giving us a glimpse into the universe's explosive birth. So, while these tiny ripples might seem like minor details, they're actually one of the most important clues we have about the universe's history. They connect the dots between the Big Bang and the cosmos we see today, helping us piece together the story of how everything came to be. And as we continue to study them, we're uncovering even more about the universe's hidden structure and the forces that shaped it. With that in mind, let's turn our attention to another incredible aspect of the CMB, how it helps us measure the universe's expansion and understand the role of dark energy in shaping our cosmic destiny. Now, let's shift our focus to how the cosmic microwave background plays a crucial role in measuring the universe's expansion. One of the most important tools in cosmology is the Hubble constant, a number that tells us how fast the universe is expanding. And guess what? The CMB is like a cosmic ruler that helps us calculate this critical value. When we look at the CMB, we're essentially seeing the universe as it was just 380,000 years after the Big Bang. The patterns in the CMB's temperature fluctuations, those anisotropies we talked about earlier, give us clues about the universe's size and shape at that time. By comparing these ancient measurements with observations of the universe today, scientists can figure out how much the universe has stretched over billions of years. Here's how it works. The CMB provides a snapshot of the early universe's density and temperature, which are directly tied to the rate of expansion. Using this data, researchers can calculate the Hubble constant by measuring how quickly galaxies are moving away from us. The farther away a galaxy is, the faster it appears to be receding, a phenomenon known as Hubble's law. The CMB helps calibrate this relationship, giving us a precise way to measure the universe's expansion rate. But here's where it gets even more interesting. The CMB doesn't just help us measure the Hubble constant, it also reveals the influence of dark energy, the mysterious force driving the universe's accelerated expansion. By studying the CMB, scientists have discovered that dark energy makes up about 68% of the universe's total energy content. This discovery has completely reshaped our understanding of the cosmos, showing that the universe isn't just expanding, it's doing so faster and faster over time. So, the CMB isn't just a relic of the past, it's a powerful tool for understanding the present and future of our universe. By helping us measure the Hubble constant and uncover the role of dark energy, the CMB gives us a clearer picture of how the universe has evolved and where it's headed. And as we continue to refine our measurements, we're getting closer to answering some of the biggest questions in cosmology, like what the ultimate fate of the universe might be. With that in mind, let's explore another fascinating aspect of the CMB, how it acts as a time capsule, allowing us to peer back into the universe's infancy and uncover the secrets of its earliest moments. Now, let's take a step back in time, way back, to explore how the cosmic microwave background acts as a cosmic time capsule. Imagine holding a photograph from the universe's earliest days, a snapshot frozen in time. That's essentially what the CMB is. It captures the universe when it was just 380,000 years old, a mere infant in cosmic terms. At this point, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This light, now stretched into microwaves due to the expansion of the universe, carries with it the imprint of those early moments. By studying the CMB, we're not just looking at ancient light, we're decoding the universe's baby pictures. The CMB reveals the conditions of the early universe in incredible detail. Those tiny temperature fluctuations we've talked about, they're like cosmic fingerprints showing us where matter was slightly denser or sparser. These variations became the seeds for everything we see today: galaxies, stars, and even the vast cosmic web that connects them. Without these fluctuations, the universe would be a featureless void. But the CMB doesn't just show us what the universe looked like, it also tells us how it evolved. By analyzing the patterns in the CMB, scientists can trace the growth of structures over billions of years. It's like watching a time-lapse video of the universe, from its chaotic beginnings to the intricate cosmic landscape we see today. What's truly remarkable is that the CMB allows us to test our theories about the universe's evolution. For example, it confirms that the universe expanded rapidly during a period called cosmic inflation, a theory that explains why the universe is so uniform on large scales. The CMB also helps us understand how dark matter and dark energy shaped the universe's growth, giving us a clearer picture of the forces at work. In a way, the CMB is like a history book written in light. It tells the story of the universe's birth, its early struggles, and its ongoing expansion. And as we continue to study it, we're uncovering new chapters in that story, revealing secrets about the universe's past and its future. With that in mind, let's turn our attention to another fascinating aspect of the CMB, how its discovery was actually predicted decades before it was found. A story that highlights the power of scientific foresight and curiosity. Now, let's shift our focus to a fascinating twist in the story of the cosmic microwave background, its prediction. Long before the CMB was accidentally discovered, brilliant minds had already foreseen its existence. In the 1940s, scientists like George Gamow and Ralph Alpher were piecing together the early history of the universe. They theorized that if the Big Bang really happened, there should be some leftover radiation from that explosive beginning. Gamow and Alpher's work was groundbreaking. They proposed that the universe began as an incredibly hot, dense state, and that as it expanded and cooled, it would leave behind a faint glow of radiation. This glow, they argued, would be stretched over time into microwaves due to the universe's expansion. It was a bold prediction, one that seemed almost impossible to test at the time. After all, how do you detect something as subtle as a faint whisper of radiation from the dawn of time? What's even more remarkable is that their prediction wasn't just a lucky guess. It was based on solid physics and mathematical calculations. Gamow and Alpher used the laws of thermodynamics and nuclear physics to estimate the temperature of this leftover radiation. They calculated that it would be around 5 Kelvin, which is incredibly close to the actual temperature of 2.7 Kelvin we observe today. But here's the kicker: when Penzias and Wilson stumbled upon the CMB in 1965, they had no idea they were confirming a decades-old prediction. In fact, it wasn't until later that the scientific community connected the dots and realized that the mysterious microwave signal they detected was exactly what gamma and alpha had predicted. This story is a testament to the power of scientific foresight. It shows how theoretical predictions can guide discoveries, even when those discoveries happen by accident. Gamma and alpha's work laid the foundation for modern cosmology, and their prediction of the CMB remains one of the most profound examples of how science can anticipate the universe's secrets long before we have the tools to uncover them. With this incredible prediction in mind, let's move on to another intriguing aspect of the CMB: how it serves as a cosmic fossil, preserving the universe's earliest moments for us to study billions of years later. Now, let's take a closer look at how the cosmic microwave background acts as a cosmic fossil, preserving the universe's earliest moments for us to study billions of years later. Just like a fossil captures a snapshot of life from millions of years ago, the CMB gives us a glimpse into the universe when it was just 380,000 years old. It's a time capsule frozen in the fabric of space, holding clues about how everything began. Think of it this way: when you look at a fossil, you're seeing the remains of a creature that lived long ago. Similarly, when we observe the CMB, we're seeing the afterglow of the Big Bang, the moment when the universe transitioned from a hot, dense soup of particles to a cooler, more transparent state. This transition allowed light to travel freely for the first time, and that light is what we detect today as the CMB. It's like a photograph of the universe in its infancy, capturing the conditions that would eventually lead to the formation of galaxies, stars, and planets. But the CMB isn't just a static image, it's a dynamic record. The tiny temperature fluctuations we see in the CMB, known as anisotropies, are like fingerprints of the early universe. These fluctuations represent regions where matter was slightly denser or less dense than average. Over billions of years, these small differences grew under the influence of gravity, eventually forming the vast cosmic structures we see today, like galaxy clusters and superclusters. In this way, the CMB isn't just a fossil, it's a blueprint for the universe's evolution. What's truly remarkable is how much information we can extract from this ancient light. By studying the CMB, scientists can determine the universe's age, its composition, and even its shape. It tells us about the balance of dark matter, dark energy, and ordinary matter, and it provides evidence for the rapid expansion of the universe during its earliest moments, known as cosmic inflation. Every detail in the CMB is a piece of the puzzle, helping us reconstruct the story of how the universe came to be. So, the next time you hear about the cosmic microwave background, think of it as more than just faint radiation. It's a cosmic fossil, a treasure trove of information that connects us to the universe's origins. And just like a fossil, it reminds us that the past is always present, waiting to be uncovered. With this in mind, let's explore how the CMB's polarization adds another layer to our understanding of the universe's first moments. Now, let's dive into another fascinating aspect of the cosmic microwave background: its polarization. Just as light can be polarized when it reflects off a surface, like sunlight bouncing off a lake, the CMB also carries a subtle polarization signal. This polarization isn't just a random feature. It's a powerful tool that helps us peer even further back in time, into the universe's very first moments. Polarization in the CMB arises from the way light interacted with matter in the early universe. When the universe was still a hot, dense plasma, photons, particles of light, were constantly scattering off electrons. As the universe expanded and cooled, electrons combined with protons to form neutral atoms, allowing photons to travel freely for the first time. But before this moment, the scattering of photons created a specific pattern of polarization, imprinted on the CMB like a cosmic fingerprint. These patterns of polarization are incredibly subtle, but they hold vital clues about the universe's infancy. One of the most exciting discoveries is that the polarization can tell us about the era of cosmic inflation. a period of rapid expansion that occurred just fractions of a second after the Big Bang. During inflation, the universe expanded faster than the speed of light, stretching quantum fluctuations into larger-scale density variations. These variations left their mark on the CMB's polarization, giving us a glimpse of the universe's earliest moments. There are two main types of polarization patterns in the CMB, E modes and B modes. E modes are easier to detect and are primarily caused by density fluctuations in the early universe. B modes, on the other hand, are much harder to observe and are thought to be generated by gravitational waves rippling through space-time during inflation. Detecting B modes would be like finding a smoking gun for cosmic inflation, providing direct evidence of this rapid expansion and helping us understand the forces that shape the universe. So far, scientists have detected E modes with great precision, but the search for B modes continues. Missions like the Planck satellite and ground-based experiments such as BICEP and the South Pole Telescope have been at the forefront of this quest. While the detection of primordial B modes remains elusive, the hunt itself has deepened our understanding of the CMB and the early universe. In essence, the polarization of the CMB is like a hidden layer of information waiting to be decoded. It not only confirms what we already know about the universe's evolution, but also opens the door to new discoveries about its origins. With each new observation, we get closer to unraveling the mysteries of cosmic inflation and the very first moments of existence. And with that, let's turn our attention to how the CMB helps us test theories of inflation, bringing us even closer to understanding the universe's dramatic beginnings. Now, shifting our focus to the role of the cosmic microwave background in testing one of the most groundbreaking theories in cosmology, cosmic inflation. The CMB doesn't just tell us about the universe's early state. It also serves as a critical testing ground for theories about how the universe expanded in its first moments. Cosmic inflation proposes that the universe underwent an exponential expansion, growing from a tiny speck to a vast expanse in a fraction of a second after the Big Bang. But how do we know this actually happened? That's where the CMB comes in. The tiny temperature fluctuations and polarization patterns in the CMB are like cosmic breadcrumbs, leading us back to the era of inflation. During this rapid expansion, quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to enormous scales. These fluctuations eventually became the seeds for the large-scale structures we see today, like galaxies and galaxy clusters. The CMB captures these imprints, allowing scientists to test whether the predictions of inflation match what we observe. One of the key predictions of inflation is the spectrum of these fluctuations. The theory suggests that the fluctuations should follow a specific pattern, known as a nearly scale invariant spectrum. Remarkably, the CMB's temperature variations align almost perfectly with this prediction, providing strong evidence for inflation. But that's not all. The polarization patterns we discussed earlier, particularly the elusive B modes, are another critical piece of the puzzle. If detected, these B modes would be a direct signature of gravitational waves generated during inflation, offering even more compelling proof. Experiments like the Planck satellite and ground-based observatories have been meticulously analyzing the CMB to test these predictions. While definitive evidence of B modes remains a challenge, the data so far has been incredibly supportive of the inflationary model. The CMB has not only confirmed the broad strokes of inflation, but also helped refine the details, such as the energy scale at which inflation occurred and the nature of the inflattened field, the hypothetical force driving this rapid expansion. In essence, the CMB acts as a cosmic laboratory, allowing us to test theories that would otherwise be impossible to probe directly. It bridges the gap between the universe's earliest moments and the structures we see today, offering a glimpse into the forces that shaped everything we know. As we continue to study the CMB, we're not just learning about the past, we're uncovering the fundamental laws that govern the universe itself. And with that, let's explore how satellites have revolutionized our ability to map the CMB with unprecedented precision. Now, let's take a closer look at how we've been able to map the cosmic microwave background with such incredible precision. This brings us to the unsung heroes of cosmology, satellites. Over the years, missions like COBE, WMAP, and Planck have revolutionized our understanding of the CMB, turning it from a faint whisper in the cosmos into a detailed map of the early universe. The journey began with the Cosmic Background Explorer, or COBE, launched in 1989. COBE was the first mission to provide a full sky map of the CMB, confirming its near uniformity and detecting those tiny temperature fluctuations we've been talking about. These findings were so groundbreaking that the team behind COBE was awarded the Nobel Prize in Physics in 2006, but COBE was just the beginning. Next came the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP took things to the next level, measuring the CMB with even greater accuracy. It refined our understanding of the universe's age, composition, and expansion rate, and its data became the gold standard for cosmology for over a decade. WMAP maps revealed the universe's geometry with unprecedented clarity, showing that it's flat on large scales, a key prediction of cosmic inflation. Then, in 2009, the Planck satellite entered the scene. Planck was designed to push the boundaries even further, with instruments sensitive enough to detect the faintest whispers of the CMB. Its mission was to measure the CMB's temperature and polarization with the highest precision ever achieved, and it delivered. Planck's data not only confirmed earlier findings but also provided new insights into the universe's composition, the nature of dark energy, and even the properties of neutrinos. It also placed tighter constraints on inflationary models, helping scientists refine their theories about the universe's earliest moments. What makes these satellites so remarkable is their ability to observe the CMB from space, free from the interference of Earth's atmosphere. This allows them to capture the CMB's faint signals with incredible clarity, providing a level of detail that ground-based observatories simply can't match. Together, COBE, WMAP, and Planck have transformed the CMB from a cosmic curiosity into one of the most powerful tools in modern cosmology. As we continue to study the CMB, these satellites remind us of the incredible ingenuity and collaboration behind our quest to understand the universe. They've not only mapped the CMB but also paved the way for future missions that will delve even deeper into the mysteries of the cosmos. And with that, let's explore how the CMB has helped us uncover the shape of the universe itself. Now, shifting our focus to the grand structure of the cosmos, let's explore how the cosmic microwave background has unveiled one of the most profound truths about our universe, its shape. The CMB isn't just a snapshot of the early universe, it's also a cosmic blueprint that reveals the geometry of space itself. And here's the fascinating part: the universe on the largest scales is flat. But what does it mean for the universe to be flat? It's not flat like a sheet of paper, but rather in the sense of its geometry. Imagine space as a giant grid where parallel lines never meet and the angles of a triangle always add up to 180 degrees. This flatness is a key prediction of the theory of cosmic inflation, which suggests that the universe expanded exponentially in its earliest moments, smoothing out any curvature. The CMB plays a crucial role in confirming this flatness. Tiny temperature fluctuations in the CMB, known as anisotropies, act like cosmic rulers. By measuring the size and distribution of these fluctuations, scientists can determine the geometry of the universe. If the universe were curved, these fluctuations would appear distorted or stretched. But the data from satellites like WMAP and Planck show that the fluctuations match the patterns expected for a flat universe with remarkable precision. This flatness has profound implications. It tells us that the total energy density of the universe is finely balanced, with just the right amount of matter, and dark energy to keep space from curving. If there were too much matter, the universe would be positively curved like a sphere, too little, and it would be negatively curved like a saddle. But the CMB shows us that the universe is just right flat, like a perfectly balanced cosmic scale. This discovery isn't just a neat fact, it's a cornerstone of modern cosmology. It supports the idea of cosmic inflation and helps us understand the universe's evolution from its earliest moments to the vast, expanding cosmos we see today. And as we continue to study the CMB, we're not just mapping the universe's past, we're uncovering the very fabric of reality itself. With that in mind, let's turn our attention to how the CMB might hold echoes of the universe's very first moments' gravitational waves. Now, let's dive into one of the most exciting frontiers in cosmology, the search for primordial gravitational waves hidden within the cosmic microwave background. These waves are like cosmic ripples, faint echoes from the universe's very first moments, and they could hold the key to understanding what happened during the era of cosmic inflation. Gravitational waves are disturbances in the fabric of spacetime caused by massive objects moving or colliding, but the ones we're talking about here are different. Primordial gravitational waves were generated during the rapid expansion of the universe just after the Big Bang, a period known as cosmic inflation. These waves would have left a unique imprint on the CMB, specifically in its polarization patterns. Polarization is a property of light that describes the direction in which its waves vibrate. In the case of the CMB, the polarization can be split into two types, E modes and B modes. E modes are caused by density fluctuations in the early universe, while B modes are the smoking gun for primordial gravitational waves. Detecting these B modes would be like finding a fingerprint from the universe's birth, providing direct evidence for cosmic inflation. The search for these B modes has been one of the most challenging endeavors in modern science. Experiments like BICEP and the Planck satellite have been at the forefront of this effort. In 2014, the BICEP team announced a potential detection of B modes, sparking excitement across the scientific community. However, further analysis revealed that the signal was likely caused by interstellar dust, not gravitational waves. This setback highlighted just how difficult it is to separate the faint signal of primordial waves from other sources of interference. Despite the challenges, the hunt continues. Future missions like the upcoming LiteBIRD satellite are being designed with even greater sensitivity to detect these elusive waves. If successful, they could confirm the theory of cosmic inflation and give us a glimpse into the universe's earliest moments, when it was just a fraction of a second old. The implications of finding primordial gravitational waves would be monumental. It would not only validate cosmic inflation, but also provide clues about the energy scales at which inflation occurred. This could help us understand the fundamental forces and particles that govern the universe at its birth, potentially bridging the gap between quantum mechanics and general relativity. So, while we haven't yet detected these cosmic ripples, the search itself is pushing the boundaries of our knowledge. The CMB remains a treasure trove of information, and with each new discovery, we're piecing together the story of how our universe began. Next, we'll explore how the CMB is helping scientists test theories that go beyond our current understanding of physics. Now, let's shift our focus to how the cosmic microwave background is not just a relic of the past, but also a powerful tool for probing the frontiers of modern physics. The CMB is like a cosmic laboratory, offering scientists a unique way to test theories that go beyond the standard model of particle physics. This includes some of the most mysterious and elusive concepts in science, like dark energy and quantum gravity. Dark energy, the mysterious force driving the accelerated expansion of the universe, is one of the biggest puzzles in cosmology. The CMB helps us study this phenomenon by providing precise measurements of the universe's expansion rate and its large-scale structure. Tiny fluctuations in the CMB's temperature and polarization reveal how dark energy has influenced the growth of cosmic structures over billions of years. By analyzing these patterns, scientists can refine their understanding of dark energy's properties and its role in shaping the universe. But the CMB's usefulness doesn't stop there. It also offers a window into the realm of quantum gravity, a theoretical framework that seeks to unify quantum mechanics and general relativity. While these two pillars of physics have been incredibly successful in their own domains, they don't play well together when it comes to explaining phenomena at the smallest scales, like the behavior of spacetime near a black hole or during the Big Bang. The CMB's polarization patterns, particularly the elusive B modes we discussed earlier, could carry signatures of quantum gravitational effects from the universe's earliest moments. Detecting these signals would be a groundbreaking step toward understanding how gravity operates at the quantum level. Experiments like the Planck satellite and future missions such as LiteBIRD are designed to push the limits of precision in CMB measurements. These missions aim to uncover subtle anomalies or deviations from the standard model predictions, which could point to new physics. For instance, if the CMB reveals unexpected patterns in the distribution of temperature or polarization, it might hint at the existence of new particles or forces that we haven't yet discovered. The CMB's role as a testing ground for new physics is a testament to its enduring importance in cosmology. It's not just a snapshot of the early universe, it's a dynamic tool that continues to challenge and refine our understanding of the cosmos. As we gather more data and develop more sophisticated instruments, the CMB will undoubtedly remain at the forefront of our quest to unravel the universe's deepest mysteries. Next, we'll explore how the CMB is gradually fading over time and what that means for the future of cosmology. Now, let's turn our attention to something truly fascinating. The cosmic microwave background is not a static relic, it's actually fading over time. As the universe continues to expand, the CMB is slowly losing its intensity, becoming weaker and colder. This might sound like a small detail, but it has profound implications for how we study the cosmos in the future. The CMB's fading is a direct consequence of the universe's expansion. As space stretches, the wavelengths of the CMB's light stretch along with it, shifting toward longer, lower-energy wavelengths. This process, known as redshift, causes the CMB to cool down even further from its already frigid temperature of 2.7 Kelvin. Over billions of years, this cooling will continue, making the CMB increasingly difficult to detect with current technology. But why does this matter? For one, it means that future generations of astronomers will have a harder time studying the CMB than we do today. The signals we're capturing now are already incredibly faint, and as the CMB dims, it will require even more sensitive instruments to observe. This raises an interesting question. Are we living in a unique window of time where the CMB is still detectable enough to provide meaningful insights? It's possible that in the distant future, the CMB could become so faint that it's nearly impossible to study, leaving future cosmologists without this crucial tool for understanding the universe's origins. This fading also has implications for the information we can extract from the CMB. As the signal weakens, the tiny temperature fluctuations and polarization patterns that reveal so much about the early universe will become harder to measure. This could limit our ability to test new theories or refine our understanding of cosmic phenomena like dark energy and inflation. In a way, the CMB's gradual disappearance is a reminder that our window into the universe's infancy is not infinite. It's a fleeting opportunity that we must make the most of while we can. Yet, even as the CMB fades, it leaves behind a legacy. The data we've already collected from missions like Planck and WMAP will continue to shape our understanding of the cosmos for decades to come. And as technology advances, we may find new ways to extract even more information from the CMB before it becomes too faint to observe. The fading of the CMB is a reminder of the universe's dynamic nature, and it underscores the importance of seizing the moment to explore its mysteries while we still can. Next, we'll dive into how the CMB serves as a window into the enigmatic force known as dark energy. Now, shifting our focus to one of the most intriguing mysteries of the cosmos, let's explore how the cosmic microwave background serves as a window into dark energy. This enigmatic force, which makes up about 68% of the universe, is responsible for the accelerated expansion of space. But how does the CMB help us understand something so elusive? The answer lies in the subtle clues embedded in the CMB's temperature fluctuations and polarization patterns. When scientists study the CMB, they're not just looking at a snapshot of the early universe, they're also uncovering hints about how the universe has evolved over billions of years. The distribution of temperature variations in the CMB provides critical information about the universe's geometry and expansion rate. By analyzing these patterns, researchers can infer the presence and influence of dark energy, which acts as a kind of cosmic pressure pushing galaxies apart faster and faster. One of the key ways the CMB sheds light on dark energy is through its role in measuring the universe's large-scale structure. The CMB's fluctuations are like seeds that grew into the vast cosmic web of galaxies and galaxy clusters we see today. By comparing the CMB's early map with the distribution of galaxies in the modern universe, scientists can track how dark energy has shaped the cosmos over time. This comparison helps them refine models of dark energy's behavior and its impact on the universe's expansion. But the CMB doesn't just tell us that dark energy exists, it also helps us understand its properties. For example, the CMB has been instrumental in confirming that dark energy behaves like a constant force, often referred to as the cosmological constant. This finding aligns with Einstein's theory of general relativity, but it also raises new questions. Why does dark energy have the specific strength it does? And could its behavior change over time? These are questions the CMB continues to help us explore. Interestingly, the CMB also provides a way to test alternative theories about dark energy. Some scientists propose that dark energy might not be a constant force, but instead a dynamic field that evolves over time. By examining the CMB's detailed patterns, researchers can look for subtle deviations from the predictions of the cosmological constant model. These deviations could point to new physics, potentially revolutionizing our understanding of dark energy and the universe itself. As we continue to study the CMB, it's clear that this ancient light holds the key to unlocking some of the deepest mysteries of the cosmos. From revealing the universe's expansion history to probing the nature of dark energy, the CMB remains an indispensable tool for cosmologists. And while dark energy remains one of the most puzzling aspects of modern science, the CMB ensures that we're not completely in the dark. It's guiding us toward answers, one photon at a time. Next, we'll uncover how the CMB is intricately linked to the cosmic web, the vast network of galaxies that defines the structure of our universe. Now, let's dive into how the cosmic microwave background is intricately linked to the cosmic web, the sprawling network of galaxies and galaxy clusters that defines the structure of our universe. The CMB isn't just a relic of the past, it's a blueprint for the universe's large-scale architecture, those tiny temperature fluctuations we've talked about. They're the seeds from which the cosmic web grew. When the universe was just a few 100,000 years old, the CMB captured the faint ripples of density variations in the early cosmos. These ripples, though incredibly small, were the starting point for everything we see today. Over billions of years, gravity took hold, pulling matter together into denser regions while leaving emptier voids in between. This process gave rise to the cosmic web, a vast network of filaments made up of galaxies and galaxy clusters connected by dark matter and gas. The CMB's fluctuations act like a cosmic fingerprint, encoding the initial conditions of the universe. By studying these patterns, scientists can trace how the universe evolved from a nearly uniform soup of particles into the intricate web of structures we observe today. The CMB's map of the early universe serves as a starting point, while observations of the cosmic web in the present day show us the end result. Together, they tell a story of cosmic evolution spanning billions of years. One of the most fascinating aspects of this connection is how the CMB helps us understand the role of dark matter in shaping the cosmic web. Dark matter, which doesn't emit light but exerts gravitational pull, makes up the backbone of the cosmic web. The CMB's fluctuations reveal how dark matter was distributed in the early universe, and by comparing this to the distribution of galaxies today, scientists can see how dark matter guided the formation of the cosmic web. It's like watching a time lapse of the universe's growth with the CMB as the first frame. But the cosmic web isn't just about galaxies and dark matter. It's also filled with vast amounts of gas, much of it too faint to see directly. The CMB helps here too. As light from the CMB travels through the cosmic web, it interacts with this gas, leaving subtle imprints that scientists can detect. These imprints provide clues about the distribution and properties of the gas, helping us piece together the full picture of the cosmic web structure. What's truly remarkable is how the CMB and the cosmic web together offer a complete view of the universe's history. The CMB shows us the starting point, while the cosmic web reveals the outcome of billions of years of cosmic evolution. By studying both, scientists can test theories about how the universe formed and evolved, from the tiniest fluctuations in the CMB to the grandest structures in the cosmos. As we continue to explore the connection between the CMB and the cosmic web, we're not just learning about the universe's past, we're uncovering the processes that shaped everything around us. From the smallest ripples in the early universe to the vast filaments of the cosmic web, the CMB remains a vital tool for understanding the cosmos. Next, we'll explore how the CMB provides insights into neutrinos, some of the most elusive particles in the universe. Now, shifting our focus to one of the most mysterious particles in the universe, let's explore how the cosmic microwave background helps us understand neutrinos. These ghostly particles, which barely interact with matter, have long puzzled scientists, but thanks to the CMB, we're starting to uncover their secrets. Neutrinos are incredibly abundant in the universe, yet they're so elusive that trillions of them pass through your body every second without you noticing. Despite their ghostly nature, neutrinos play a crucial role in shaping the cosmos. The CMB provides a unique window into their properties, particularly their mass and abundance. When the universe was young and the CMB was forming, neutrinos were zipping around at nearly the speed of light, influencing how matter clumped together in the early universe. The CMB's temperature fluctuations hold subtle clues about these particles. Because neutrinos move so quickly, they tend to smooth out small-scale variations in the density of matter. This effect leaves a distinct imprint on the CMB, allowing scientists to estimate the total mass of neutrinos in the universe. While we know neutrinos have mass, they're incredibly light, so light that their exact mass has been one of the biggest mysteries in particle physics. The CMB helps narrow down the possibilities, giving us a clearer picture of how these particles fit into the cosmic puzzle. But it's not just about mass. The CMB also tells us about the number of neutrino species in the universe. Early measurements suggested there were 3 types of neutrinos, but the CMB has allowed scientists to confirm this with remarkable precision. By studying the CMB's patterns, researchers can rule out the existence of additional neutrino-like particles, helping us refine our understanding of the fundamental building blocks of the universe. What's truly fascinating is how the CMB connects neutrinos to the larger story of cosmic evolution. These particles, though tiny, had a significant impact on how the universe grew and structured itself. By studying the CMB, we're not just learning about neutrinos, we're uncovering how they shaped the cosmos from its earliest moments. It's a reminder that even the smallest particles can leave a lasting mark on the universe. As we continue to study the CMB, we're gaining new insights into neutrinos and their role in the cosmos. these elusive particles, once thought to be nearly impossible to detect, are now revealing their secrets thanks to the light from the early universe. Next, we'll turn our attention to how the CMB acts as a cosmic thermometer, helping us measure the temperature of the universe across billions of years. Now, let's take a closer look at how the cosmic microwave background serves as a cosmic thermometer, offering us a way to measure the temperature of the universe across its vast history. The CMB is more than just a snapshot of the early universe. It's a precise tool that allows scientists to track how the universe has cooled over billions of years. When the CMB was first emitted, the universe was incredibly hot, filled with a dense, glowing plasma. As the universe expanded, it cooled, and the light from that plasma stretched into the microwave wavelengths we detect today. The temperature of the CMB, which is now just 2.7 Kelvin, or about -270.45 degrees Celsius, is a direct reflection of this cooling process. This temperature is remarkably uniform, but the tiny fluctuations within it tell a deeper story about the universe's thermal evolution. By mapping these temperature variations, scientists can trace how the universe transitioned from a hot, dense state to the cooler, more diffuse cosmos we see today. The CMB's temperature measurements also help us understand key events in the universe's history, such as the formation of the first atoms and the era of reionization, when the first stars and galaxies lit up the cosmos. These events left subtle imprints on the CMB, allowing us to piece together a timeline of the universe's thermal changes. What's truly remarkable is how the CMB's temperature acts as a benchmark for other cosmic measurements. For example, by comparing the CMB's temperature to the temperatures of distant gas clouds or galaxy clusters, scientists can test theories about how the universe has evolved. This makes the CMB not just a thermometer, but a cornerstone of modern cosmology, helping us understand the universe's past, present, and even its future. As we continue to study the CMB, we're uncovering more about how the universe has cooled and expanded over time. It's a testament to the power of this ancient light, which continues to illuminate the secrets of our cosmic origins. Next, we'll dive into the mysteries that still surround the CMB and what they might reveal about the universe's deepest questions. Now, as we turn our attention to the final piece of this cosmic puzzle, it's important to recognize that the cosmic microwave background, while incredibly revealing, still holds many mysteries waiting to be unraveled. Despite all we've learned, the CMB continues to challenge our understanding of the universe, leaving scientists with profound questions that push the boundaries of modern cosmology. One of the biggest mysteries tied to the CMB is the nature of dark matter. While we know dark matter makes up about 27% of the universe's total energy and matter, we still don't know what it actually is. The CMB provides clues about how dark matter influenced the early universe's structure, but its true identity remains elusive. Is it made of particles we haven't discovered yet? Or does it represent something entirely new in the realm of physics? These are questions the CMB helps us ask, even if it hasn't yet provided the answers. Another major puzzle is the origin of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. The CMB's patterns support the idea that inflation happened, but we don't fully understand what caused it or how it worked. Was it driven by a new kind of energy field, or is there a deeper mechanism at play that we haven't even imagined? The CMB's subtle fluctuations hint at these possibilities, but they also remind us how much we still have to learn. And then there's the mystery of dark energy, the force driving the universe's accelerated expansion. The CMB helps us measure its effects, but we're still in the dark about what dark energy actually is. Is it a property of space itself, or is it something entirely different? The CMB's temperature and polarization patterns offer tantalizing clues, but they also underscore how much remains unknown. Even the CMB's own fading over time raises questions. As the universe expands, the CMB grows weaker, and in the distant future, it may become undetectable. What will that mean for our ability to study the early universe? And what other tools will we need to uncover the secrets the CMB can no longer reveal? These unanswered questions remind us that the CMB is not just a relic of the past, it's a gateway to the future of cosmology. Every mystery it presents is an opportunity for discovery, pushing us to develop new theories, build better instruments, and explore the universe in ways we haven't yet imagined. The CMB is a reminder that the universe is full of surprises, and the more we learn, the more we realize how much we still have to uncover. With that, we've reached the end of our journey through 25 fascinating facts about the cosmic microwave background. But the story of the CMB is far from over. As we continue to study this ancient light, who knows what new mysteries and answers it will reveal. Now, let's venture into one of the most mind-bending ideas in modern cosmology: how the cosmic microwave background might hold clues about the existence of other universes beyond our own. The concept of a multiverse, a vast collection of parallel universes, has long been a topic of speculation and debate. But could the CMB actually offer evidence for such a radical idea? The answer lies in the subtle patterns and anomalies found in the CMB's temperature fluctuations. While most of these variations align with our current understanding of the universe, some features don't quite fit. For instance, certain large-scale patterns in the CMB appear oddly aligned or asymmetrical, which some scientists suggest could be the imprint of interactions with other universes. These anomalies, though still unexplained, open the door to the possibility that our universe isn't alone. One intriguing theory is that during cosmic inflation, the rapid expansion of the early universe bubbles of space-time may have formed, each giving rise to its own universe. If these bubbles collided or interacted, they could have left faint traces in the CMB. While this idea is still speculative, it's a fascinating example of how the CMB might serve as a cosmic detective, uncovering clues about realities beyond our own. Another angle comes from the study of dark energy. If dark energy behaves differently in other universes, it could influence the way those universes expand and evolve. The CMB's measurements of dark energy in our universe might help us infer how it operates elsewhere, offering indirect hints about the nature of a multiverse. Of course, the multiverse theory remains highly controversial, and the evidence from the CMB is far from conclusive, but that's part of what makes it so exciting. The CMB doesn't just tell us about the universe we live in, it challenges us to think bigger, to consider the possibility that our cosmos is just one piece of a much larger puzzle. As we continue to study the CMB with ever more advanced tools, who knows what we might discover? Could the faint whispers of other universes be hiding in the ancient light of the CMB? Only time and a lot of scientific ingenuity will tell. This brings us to the next chapter in our exploration of the cosmic microwave background, where we'll look at how future missions and technologies are set to deepen our understanding of this incredible cosmic relic. Now, let's turn our gaze toward the horizon of discovery, where the future of cosmology promises to unlock even more secrets hidden within the cosmic microwave background. As technology advances, so too does our ability to probe the ancient light of the CMB with unprecedented precision. What lies ahead could revolutionize our understanding of the universe and its origins. One of the most exciting developments on the horizon is the next generation of space-based observatories. Missions like the proposed LiteBIRD and CMB S4 aim to map the CMB with even greater detail, focusing on its polarization patterns. These subtle ripples in the CMB's light could reveal the fingerprints of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. By studying these patterns, scientists hope to confirm whether inflation truly occurred, and if so, what drove it. Ground-based experiments are also pushing the boundaries of what we can learn from the CMB. Advanced telescopes equipped with highly sensitive detectors are being built in some of the most remote and pristine locations on Earth, such as the Atacama Desert and the South Pole. These instruments will measure the CMB's temperature fluctuations with incredible accuracy, helping us refine our understanding of the universe's composition, including the elusive dark matter and dark energy. But it's not just about better instruments, it's also about smarter ways to analyze the data. Machine learning and artificial intelligence are playing an increasingly important role in cosmology. These tools can sift through vast amounts of CMB data, identifying patterns and anomalies that might otherwise go unnoticed. This could lead to groundbreaking discoveries, such as new insights into the nature of neutrinos or even the detection of primordial gravitational waves, which would provide direct evidence of cosmic inflation. Looking further ahead, some scientists are exploring the possibility of using quantum technologies to study the CMB. Quantum sensors, with their extraordinary sensitivity, could detect minute variations in the CMB's temperature and polarization, offering a new window into the early universe. While still in its infancy, this approach could open up entirely new avenues of research, potentially uncovering phenomena we haven't even imagined yet. The future of cosmology is not just about answering the questions we already have. It's about discovering new ones. As we delve deeper into the CMB, we may find clues that challenge our current theories, forcing us to rethink our understanding of the cosmos. Each new mission, each technological leap, brings us closer to unraveling the mysteries of the universe's birth and evolution. So, what does the future hold for our exploration of the CMB? With every advancement, we inch closer to understanding the universe's deepest secrets. And as we do, we're reminded that the CMB is more than just a relic of the past. It's a guide to the future, pointing the way toward discoveries that could reshape our understanding of reality itself. This brings us to the final chapter of our journey, where we'll explore how the cosmic microwave background has made its way into popular culture, becoming a symbol of humanity's quest to understand the cosmos. Now, let's take a step into the world of storytelling and imagination, where the cosmic microwave background has found its way into popular culture. While it might seem like a highly scientific concept, the CMB has captured the curiosity of creators in movies, television, and literature, becoming a symbol of humanity's fascination with the cosmos. One of the most notable appearances of the CMB is in the 2014 science fiction film Interstellar. In this visually stunning movie, the CMB is subtly referenced as part of the broader exploration of space and time. The film's portrayal of black holes, wormholes, and the fabric of the universe draws on real scientific concepts, including the CMB, to create a sense of awe and wonder. It's a perfect example of how complex ideas from cosmology can inspire compelling narratives that resonate with audiences. Television has also embraced the CMB, particularly in shows that blend science with drama. In the popular series The Big Bang Theory, the CMB is occasionally mentioned in the context of the characters' scientific discussions. While the show is primarily a comedy, its inclusion of real scientific concepts like the CMB helps bridge the gap between entertainment and education, making these ideas more accessible to a broader audience. Books, too, have explored the CMB in creative ways. In The Fabric of the Cosmos by physicist Brian Greene, the CMB is described as a key piece of evidence for understanding the universe's origins. Greene's ability to explain complex topics in an engaging and relatable manner has made the CMB a topic of interest for readers who might not have a background in science. Similarly, science fiction novels often use the CMB as a backdrop for stories about the universe's mysteries, weaving it into plots that explore the nature of reality itself. Even beyond traditional media, the CMB has made its mark. Video games like Mass Effect and No Man's Sky incorporate elements of cosmology, including references to the CMB, to create immersive worlds that reflect humanity's quest to understand the cosmos. These games allow players to explore the universe in ways that are both entertaining and thought-provoking, blending science with interactive storytelling. The CMB's presence in popular culture highlights its significance not just as a scientific discovery, but as a symbol of our collective curiosity about the universe. By appearing in movies, TV shows, books, and even video games, the CMB has become a part of mainstream culture, reminding us that the mysteries of the cosmos are not just for scientists, they're for everyone. As we wrap up this exploration of the CMB's cultural impact, we're reminded that science and storytelling are deeply intertwined. The CMB, with its ancient light and cosmic secrets, continues to inspire creators and audiences alike, proving that the universe's wonders are as much a source of art as they are of knowledge. This brings us to the conclusion of our journey through the 25 fascinating facts about the cosmic microwave background, where we'll reflect on what we've learned and why it matters. As we reach the end of our cosmic journey, let's take a moment to reflect on the incredible story of the cosmic microwave background. From its origins as the oldest light in the universe to its role as a cosmic fossil preserving the secrets of the Big Bang, the CMB has proven to be one of the most profound discoveries in science. We've explored how it reveals the universe's composition, maps its expansion, and even hints at the existence of dark energy and primordial gravitational waves. It's a tool that has reshaped our understanding of the cosmos, offering insights into everything from the shape of the universe to the nature of neutrinos. But the CMB isn't just a scientific marvel, it's a testament to human curiosity and ingenuity. From its accidental discovery by Penzias and Wilson to the cutting-edge missions like COBE, WMAP, and Planck that have mapped it with astonishing precision, the CMB reminds us of our relentless drive to uncover the mysteries of the universe. It's a story of collaboration, innovation, and the unyielding pursuit of knowledge. And let's not forget its cultural impact. Whether it's inspiring blockbuster movies, sparking discussions in TV shows, or fueling the imaginations of authors and game developers, the CMB has transcended the realm of science to become a symbol of our shared fascination with the cosmos. It's a reminder that the universe's wonders are not just for scientists, they are for all of us to explore and marvel at. So, what have we learned? The cosmic microwave background is more than just a faint glow in the sky. It's a window into the universe's infancy, a cosmic time capsule, and a key to unlocking some of the biggest questions in science. It's a story that continues to unfold, with new discoveries and mysteries waiting to be uncovered. Now it's your turn to join the conversation. What fascinates you most about the CMB? Do you have any questions about its role in cosmology or its cultural significance? Share your thoughts in the comments below. We'd love to hear from you. And if you enjoyed this deep dive into the cosmic microwave background, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss out on exploring the wonders of the universe. Thanks for watching, and until next time, keep looking up.